Hi again, everybody. Welcome back. This last example in chapter 11 right here is actually example number 12, not example 11. We keep changing the numbers. But this deals with something that should be very familiar to you, I think, and that is a Ferris wheel. If you've never gone up on a Ferris wheel, they're pretty cool. They're not super exciting like roller coasters, but they do afford some nice views and also do give you sort of a sense of weightlessness or near weightlessness, especially depending on how fast your Ferris wheel is going. But the fact remains that your weight, your apparent weight, does change depending where on the Ferris wheel you actually are, whether you're at the top or at the bottom right here. Now this Ferris wheel has, it looks like each of the pods right here has a roof on it or something like that. But what we're going to do is we're going to kind of pretend that there is no roof on these pods, and so I'm going to draw just sort of like an upside down U for all these right here. All right, so it's like it's got a floor and maybe some walls, but no roof. So you could conceivably fly out if this Ferris wheel was going fast enough. Well, we don't want that to happen. And you can see right here, what's the minimum period such that the rider would not lose contact with their seat. Okay, so we're going to solve for that. But the point here is, what is keeping the people on the top right here, in the top of the Ferris wheel, what is keeping them in that circular path? Because there's no, I can't say that there's no normal force, but there is no, you might say there's no wall from the outside holding them in, right? They're actually on top of a wall right here, and they could easily fly out. So this person, I'll draw them in red. This person right here, kind of standing on this floor, right there, could fly out. Well, what is keeping that person in? What's keeping that person, you might say, what is being directed centripetally to keep them in? Well, it's actually their gravity, all right? mg. Of course, at some point, you could be moving fast enough such that that centripetal acceleration required to keep them in exceeds their gravity and they could fly out. Well, we don't want that. We want them to remain stuck to their seat. But what is the force that is acting against gravity to give them their perceived weight? Well, it's their normal force, right? We talked about normal force being kind of a, call it n top right there. That's the apparent weight at the top. Right, and so we're going to solve for that for part A and also for part B as well. For part C, the minimum period such that the rider would not lose contact with their seat. Well, if it's going around faster and faster and faster, those riders would probably feel less and less and less heavy to the point where if they come up off their seat at this right here, let's see, lose contact, normal force equals, well, I should say normal force is less than 0 newtons. So in part C, what we'll do is we'll solve for normal force being 0 because that means that there is basically no pressure between these riders' behinds and their seat. And that means it's a maximum speed that you can go before they start to lift up off their seat and possibly fly out. Okay? So that's the premise upon which we're going to solve for the apparent weights at part A, at the top, at the bottom, and also the minimum period, the minimum. Actually, I think I said speed before. We're looking at actually period. Okay. So let's shrink this down a little bit, and we'll make some sense of this. So I'm going to just go ahead and draw another Ferris wheel. Pretty simplified one. It's not a bad one. I started out an okay circle. We'll draw a pod at the top and a pod at the bottom. So there's kind of our roofless pod there, and at the bottom, there's our roofless pod, and we'll draw a person standing in it. Kind of a lousy person. That's okay. All right, so at the top, TOP, right here. What is the apparent weight at the top of the Ferris wheel? Okay. Well, let's sum up all the forces that exist on this person at the top of the Ferris wheel. The net centripetal force at the top. Well, what force do we have acting on them? Well, there's gravity, right? mg. directed straight down. There is also some normal force. That is the force between their feet and the floor. We'll call that N top. That force is acting upwards to give them the feeling that there's some pressure between the floor and their feet. All right? Now, which one is which direction? Well, remember, towards the center is always positive. So when we sum up our forces, that means the mg is going to be positive, mg, and that the normal force at the top is going to be negative. All right? Well, these are our component forces, we can think of it as. Let's make a statement for the net centripetal force at the top with respect to centripetal acceleration. Well, we know that that's MAC, right? So these two statements being equal, we can set them equal to each other. So mg minus normal force at the top. And remember, the normal force is really their apparent weight, right? It's the force between the bottoms of their feet and the deck or whatever they're standing on. We're going to be solving for that. Set that equal to mass times centripetal acceleration. All right? Now, we don't really know centripetal acceleration yet. We don't know that value. But we do know a couple things. We have the radius, and we have a time period. So let's write this in a little more detail. In fact, I'm going to solve for normal force at the top first. So I'm going to add this over here, and then I'm going to subtract this over. So normal force at the top equals mg minus m times centripetal acceleration. All right, and this right here, we can write in a little more detail. Like I said before, we have the period and we have the radius. So mg minus mass times what? What's an equation we have for period and radius? Well, that would be 4 pi squared r over our time period squared, right? That is one of our equations for centripetal acceleration. Great, we have it written to solve for a normal force at the top. All we need to do is plug in what we know and solve for it. All right. The mass of our person, in fact, I could have factored that mass out, but that's all right, is what's the mass of the person? 55 kilograms. 55 times 9.81. Sorry, I'm leaving my units out. Minus 55, again, that mass out front right there, times the quantity 4 pi squared times the radius. What's the radius? 7.2 meters, right? All over our time period squared, 28 seconds squared. All right? Let's see what we get. Let's find out what the normal force, or that is their apparent weight, is at the top of the Ferris wheel. And I get a grand total of 520 newtons. I'm rounding it up to the nearest whole newton. All right? That's how much they feel like they weigh at the top. Now, remember, at the top, when you're going up over the top, you kind of feel like you weigh a little bit less. So when we calculate at the bottom right there, down here, we should expect that you would weigh a little bit more.